a center here in upstate New York. We have been working with this center for 2 years for now. And this is a National Science Foundation center. They gave us a couple of years ago $3 million for 4 years in order to develop the workforce needed for this part of the world. Okay, we want to instill into from K-12 and community colleges and colleges. We want to instill in the young people the idea that nanotechnology and semiconductor is very important, in particular in this part of the world. So what we have been doing is we have been developing material for high schools and for K-12. We are going to start developing material now for community colleges. And one of the things that we have been doing is trying to bring equipment like this one. This is an atomic force microscope in order to lend it to institutions around this capital region whenever they need it. We are planning. You can see that this device is portable. We just put it into a very sturdy luggage, and we can send it any place. What we are going to try to do with this for this one, and we are going to buy another one very soon, is to create labs, create activities for high schools, for even K-12, so the teachers can learn how to use it and they can embed this into the classroom. Okay, this is a very sophisticated device, and what we are going to do today is I'm going to make a presentation of what is an atomic force microscope, and then we have here the Shreida. She worked for the Nanoscience company in Phoenix, Arizona, but it's a company from Switzerland, isn't it? They are the people who manufacture these devices here. So after my lecture, she, who is an expert in AFM, she did your PhD in AFM, so she will give us some hands-on activities, okay? And I want you to come and see what we can do. We have a lot of samples of every type, and we want to see how we can look at a sample almost at the atomic level. You can see pictures, okay? So let me give you a very fast explanation of the AFM. How many of you know what is an AFM? Oh, you will help me today, okay? So this will be basically the outline. We're going to give you some motivation on how it works, mainly, the most important thing, most probably. The reason to use a microscope of this type is simply because in nanotechnology and semiconductor, we have to deal with very small devices, or very small particles, and we want to look at them, okay? And before 1980, we couldn't do that. We couldn't do it very well, I would say, okay? So, and look at the scale of the sizes that we can see with the microscope. The AFM is one of the type scanning probe microscope. It's a family of microscopes that you can create images by scanning the sample, either by scanning the sample by touching the sample, or even without touching the sample as well, okay? Probably the most important of all the scanning probe microscope, most important because it is more used right now, is the AFM. AFM is one of them, okay? And these are the motivation, okay? We want to create pictures of little things, even at the atomic level, and see. We can even see a crystal of silicon. I don't know if I have the picture here, but you can see actually the structure of the silicon crystal, something that we couldn't do and see before. Okay. And then we can look at the live system, like you can look at the blood red cells and other things. Okay, So this is the story. It was around in the middle of 1980 in Switzerland. Actually, 3 scientists from IBM, IBM in Zurich, they created the first scanning tunnel microscope. And they 4 years later they won the Nobel Prize, which is something unusual. Okay, you do something good and you have to wait until you are 70 or 80 to get the Nobel Prize. Okay, but these guys they got it in 4 years. Then in Stanford University, one of the inventors of this, he was working there, and they made a small change to the scanning tunnel microscope, and they invented the AFM. The AFM is less bulky, easier to use, and it doesn't produce exactly resolution at the level of atoms, but it is good for nanotechnology as well. Okay, here you have a look at this little picture. You can see this is from the University of Surrey in UK. This is a cell, a collagen, and you can see the structure in the. You can see the topology. Okay, and look at the size of this 300 nanometers we have. Look how, okay, thank you. So how the atomic force microscope works? It is relatively a very simple, conceptually a very simple device. You have a cantilever, okay? A cantilever is a very small cantilever, and the cantilever has a small tip. Okay, very fine tip. The finer, the better. Okay, so and you can see it from here. Okay, this is the cantilever here, and this is the pin, and this is the sample. Okay, and the way it works that the AFM will start rastering, will start moving on the surface of the sample. And with the other mechanism that we see there, we can actually create a 3-dimensional picture of what the tip is actually touching or going through. I will give you a better. So basically, this is the type. Normally, there are different types of operation of this device, but in one type of operation, the tip, you know, when you have at the atomic level, when you have any two materials, you have electrons, and they have attraction and repulsion. So there is a force between the tip and the sample. There is actually a force that we can measure. Actually, we can measure with the AFM, and we can make a plot of it. Okay. So one important thing about the AFM is that the force between the tip and the sample at any moment should be constant, if possible. Okay. And we do this with a mechanism called feedback. We have a control system to make sure that the force between the tip and the sample remains constant. Okay. I'll look at all the parts of AFM. So here you have the sample. This is the cantilever. Here you have the tip. Here you have the sample. And we have a laser beam, a laser, normally a diode laser, which is pointing continuously to the tip of the cantilever. Okay? And you can see that because there is a light on the cantilever, and you are moving the cantilever, and the cantilever will move up and down. Then the light produced by the laser will impinge here on a mirror, and because you have the pin is moving up and down, the light will also move up and down. And then we program the light here. There's a photo detector here. It will detect this. We'll send this to a data collector, if you want, like where you can process it, and then you can, based on, depending on the software that you have, you can make a nice picture of this. Okay, so this is basically what it is. Okay, So as the cantilever moves, it moves. It will create the picture. But look at the level. What really happened from the point of view of physics? Okay, you know, when you have the tip close to the sample, basically you have forces, many type of forces. Okay, but the most important forces that you are going to experiment between the tip and the sample are the Coulombic forces, which are repulsive. Okay, because you have electrons in the pin, you have electrons in the sample, and when you put them very close together, a force of repulsion will appear. Okay, so when you are very close, you will experiment this Coulombic force. But also there is a force called the van der Waals. I'm sure you have seen this. You have teach this your student about it. It is a force that it has to do with the dipole interaction of electrons. Okay, you have dipole, and this force. This force is the repulsive force. This is a Coulombic force, and this happens when you are at a very short, when the tip is at a very short distance from the sample. Okay, the closer you have, the more force you see. And you can see it in the graphic here. Okay, this is distance here. This is force. If you are very far away from the sample, the force is very small. As long as you are approaching approaching the sample with the tip, the force will go very high. Okay, and then you have this is what we call repulsive force. Okay, at the same time we have the van der Waals interactions. Okay, this is an attractive force. Basically, it is between dipoles inside the material, and you can see that if you are far away, the force is very small, and then if you are very close, you will have a force of attraction, a big force of attraction. The actual force between the tip and the sample is a combination of these two. There are other forces as well, but these are the most important. So if you add this plus this, you're going to get this. This is actually the actual profile of the force as a function of distance, and this force will allow us to move the laser beam and make actually the picture. Okay, and you can see this. You can read this a little bit. These are basically the interaction that happened. Okay, if when you are pushing the tip toward the sample, you have the van der Waals forces attracting the tip to the sample, and at the same time you have the Coulombic forces making the repulsion. Okay. There are other forces as well, but basically these are the most important. Are we going to see the force? We can do it here. With this, we can make the plot of the force. No, yeah. With this AFM, you can actually generate this picture for a particular sample, and we're going to see it today. Okay. So these are basically the behavior of the tip. You have to remember that we are not talking about a distance like this. We're talking about a distance close to atomic distance. So everything is different at this side. Okay, but these are the things that we have to have in a system. The cantilever has to be very flexible. The cantilever actually is like a spring. Okay, it will move and vibrate at a very high speed. We're going to see it now. We need to have isolation for the device. Here we don't have the perfect isolation, but I hope will be better than yesterday. And we can detect actually the force indirectly. Okay. The cantilever is basically like this. It's like a spring. Okay. When the pin is touching or not touching the the sample, it actually vibrates. And it is unbelievable at the resonance frequency of these devices. They go from 50,000 kilohertz to 500,000 kilohertz. I wanted to think about the speed of these devices, okay? And I took this picture from your site, okay? So basically we can operate the device in 3 different ways, okay? One way is we can have the pin in contact all the time on the sample. So while the pin is moving, it is actually in contact all the time with a constant force, of course, okay? This is not the best way to do it because you can destroy the tip or you can destroy part of the sample if the force is too much. But and look at the diagram of the force, the forces in this diagram. If we have contact, this is look at it, we have a lot of force of attraction, okay, a big force. The other way we have we call it dynamic mode, which basically where the pin is not in contact with the sample. One mode of the non-contact is to have the pin moving at the same distance from the sample all the time, so it will move, it will follow the contour of the sample, but it will never touch it, okay? Another way, probably better, is what we call tapping, okay? You can have the pin, the tip, just touching the sample once in a while. Just touch the sample and then move the tip on, and then move a little bit and move, touch again, and then and it does this all the time. Okay, this is a intermittent mode, so it is only in contact at a certain point, and then and you can see that the diagram that the cantilever will move at a very high frequency. Okay. And you can see this is the range of forces in the graph for non-contact, and the intermittent will be between this and this, because sometimes you have to the pin will touch the sample. Okay.
And as for tip, I mean, to maintain the life of the tip, that's why you would not want to have continual and sample. Prevent the contact.
Sometimes you want the contact. You want to have contact. For example, for solid, we use for contact. As long as you don't destroy the sample or you don't, the tip is not. But probably this is the best way to do it.
For biological samples,
yeah,
and for like new samples, like nanoparticles and stuff, the contact lens can actually like slice through DNA, and
yeah,
it's that hard. So for that, you want something.
Yeah, it will interfere with the sample. Okay. Yesterday we were doing an experiment here, and I destroyed what I was doing this. You will see it's very delicate, and I moved the tip too fast, so I got in touch with the sample and we believe that. But yeah, so this is probably the best way to do it. This is with the cantilever is moving, touching and moving, and this one is in this way only at the same distance all the time. Okay, it is very important to control. If we use this, to control the distance and the force. We want it is important for a good sample to have the force constant, and we do this with a control system, as I told you before. Okay. There are other ways to operate this. These are the 3 important. I took this from your. Sometimes you don't want to do only a contour or a picture. For example, if you may want to find about the composition of the sample. Okay, and we use what is the phase. We can actually, this device can measure the phase of the force, and the phase will tell you something about the composition of the sample. And there are other type of measurement. depending on what you want to do. For example, if you want to do microelectronics, normally we use a mode called electrostatic force. And for example, we can measure the p-n junction, the depth, and so forth. Okay. Well, there are many ways, but basically these are the three most important, or two. Okay. Let me open this here. Are you familiar with Hooke's law in physics? Okay. This is the way that we actually measure the force. Okay. Because the force is nothing more than the force of interaction between two components and a distance. Okay, so it's like a spring. Okay, at the atomic level, being the tip being at a particular distance means that even you are pushing the string, the spring or making. So this is actually the way the device calculates the. We need feedback regulation to have a constant distance or a constant force. Okay, we use a very simple control system, a PID. Who's familiar with controllers? We're going to see here in this. We have this is the PID we have, no? A type of control system, a feedback control system called PID, and it is very important. So if, for example, the tip is too far away, the controller will move it close, and in all the process, the distance will be the same. Okay. We need. We can measure the voltage between the sample and the tip. So it is very important to track force and distance at all times, but this makes a little bit more complicated the system. Okay. For the non-contact mode, you can see that the cantilever normally will oscillate if it is non-contact, and the oscillation can be measured. We're going to see how we can measure the oscillation. You know, because the tip is like a spring, and you know that anything, the word spring in particular, they have something called the resonant frequency. Okay, and the resonant frequency of these tips are what, the 180,000, 50,000 kilohertz. So they are, and the vibration when the tip is measuring it sometimes is even higher than that. Okay. For the non-contact force, that's what is a way. Very good for semiconductors. Okay, if you don't want to destroy the chips. Okay, I think for my student, I think we have a sample. I'm going to show you in my class next semester. Sample of a semiconductor. No, yeah. So we're going to make an experiment about this. Okay. We cannot use this in fluid. Okay. And then here you have the tapping mode. Okay. So I will make this PowerPoint presentation available in our website, so you can download it anytime. Okay. Probably 1 week or 10 days after the conference. Okay. So you can use them in your classes without any problem. Okay. So we are going to make them. I'll look at the typical frequency of the cantilever. Okay. These little things. Okay. Okay. So. Okay, here you have a little table about the advantages and disadvantages. Okay, so for this, you can see that tapping mode has the less number of disadvantages, but probably a little bit slower, but it's okay. This is what we do here today. We're going to do the tapping mode. Yeah, okay, so we're going to do the measuring with tapping mode, and you will see in the computer the frequency and the phase and everything being calculated. Okay, and And I'm not going to go through this a lot, but you should see how we can measure force here, okay? And basically, we measure force by having a laser beam here, and the force here will depend on the position of the pin. So the light will change here. If you have a mirror here, the beam will impinge in different parts of this mirror or this collector, and we have a calibration curve, so we know exactly what is the force. If it is impinging here, we can find out the force and so forth and so on. So this is the way to measure indirectly force. And the way that we generate the image, as I told you before, is because the beam that goes to the detector moves. Okay, so and we have now sophisticated software that we can make pictures without any problem. Okay, this is the way that the tip scans. Okay, a typical scanning. Okay, and then just for the sake of technical. Look at the type of tips and cantilever that we have, okay? Look at these are typical tips like pyramid, okay? And normally we have silicon here, the tips. They're silicon or nano. There are some right now of nanotubes. Oh, yeah. Yeah, but they are more expensive, yeah? So basically there are many ways to do the tip. However, the thinner the tip is, the more resolution you get. Okay, so right now there is a lot of research going on in actually making these tips very, very, very fine. Okay, in order to have better resolution. I know a couple of friends at RPI who is trying to develop a very thin pin. Okay. Here you have some other picture. Look at the size of the cantilever here, 13 micrometers. We can see it. And the tip is, the height of the tip is 100, around 100 in this particular case. And I just put this for the sake of when you download the PowerPoint presentation, so you have more information. But this is basically the way that we make deflect the cantilever, okay? And then we have the feedback system, which is a controller, as I told you, because we need to control parameters. We need to control parameters that should remain constant throughout the scanning, okay? And we use a controller, correct? Here you have some applications. Okay, I don't know if you are from you or from this. Yeah, you sent me. These are actual, but made with this, no? So this is an actual picture made with this little device. Okay, in NanoSurf. Are you familiar with this? You could probably. Look at the resolution of this picture. We're talking about here micrometers or nanometers. Okay, so.
Can I ask a question? I'm just curious. With my students, I'm trying to get them to be able to go from what they can kind of understand with regular microscopes, because they look at these and they say, yeah, okay, whatever, that's nice, but they don't understand the resolution from what.
Absolutely, yeah.
Microscopic view all the way down to the submicroscopic, so that the kids can really see the
Yeah.
magnifying glass, and I think they did butterfly wings.
Yeah, it is very important. It is very, yeah, it is very important before the kid, if you show this to a kid, say, well, what is this? But it's very important that before to show them this picture, you have to teach them about the nanoscale, okay? And there are many places in the web, probably you are going to develop one. I have seen many YouTube, which show you some from an elephant, and the kids, they show them a smaller thing and smaller thing. But the important thing is to instill in the mind of these young people, and all people as well, what this means. You know, this is not simply a picture. You know, we are looking at the very nature of at almost the atomic level. You know, it's very difficult to understand, but it is part of the education. You know, but yeah. And here we have a polymer. Look at this. Yeah. So this is yours also, no? This is this is Robert actually. Look at the resolution of these things. These are not paints or anything. These are the real life. Yeah.
Is that the width of one pass of the needle? Would that be one pass of the
No, the needle passes like like when you paint the display. Lines, okay, like this. It's like painting a display. Yeah, and that's why you get this 3 dimension. You will see it in a minute in real time, in a real device, okay? Yeah.
So for the XY resolution, for this particular system, the specs say it's about 5 nanometers. I've had things with a resolution of 10.
It's 5 to 10 nanometers, yeah. So you can, which is not bad for this the size of device, okay? So.
And at that resolution, you need a little bit better vibration isolation.
Yeah. Another one. One way to measure the conductivity. Normally we do a power 4-point probe, remember? But here you can actually have the picture, okay? Have the picture of you know, conductivity has to do with the shape of things, okay? So. Here. This is if you want to measure the conductivity at different points, no? You know, the conductivity has to do with the geometry, okay? So if you have a higher bump here, you have more resistivity, so less conductivity than a hole. So
is that metallic? Is that copper or?
Oh.
No, it's like a conductive, like flexible display kind of structure. Not exactly sure, because a lot of these come from companies which have very strict. It's not exactly say what materials they are, but basically looking at the surface, you can pick out regions which are more conductive and which are less conductive, and how uniform the conductivity of the surface is. So you use a conductive AFM probe and you map the conductivity of the sample.
You can measure picoamps. So this is a small. Now, I wish the next slides are simply directly from your site. Here you will see actual application for the NIO AFM, which is this one here. Okay, so if you want to buy one of these, I'm not going to make a sales pitch here, but this is the company, okay, the Nanoscience, which is very famous, okay, in this business. So look at what we can do: metrology analysis of roughness, and we can find out if there are certain particles in a sample, or we can characterize a nanotube. I think we have a sample here, part of the show. So surface metrology. Okay, so measuring the this is distance and this is height. Okay, you can measure the roughness. This is an actual picture, no, from the Nile. So. You can count particles, which we cannot do otherwise, or we analyze them. And we have a nanotube. We have a sample here. I will show you at least in the semester. I will show you a nanotube. Okay. Okay. So this is basically what it is. But the most important thing for especially for teachers and educators, you know, we're going to make this available to any school or any college, just by we're going to set up a mechanism where you will ask for the device, and we're going to send it to you for a couple of weeks or to use. Okay, but the most important thing is that you will have to be trained how to use it, and I will be giving some training, and Fred Esterniza, who took the training yesterday with me, we're going to, if you're interested, in other words, to show it to your student and take it to your school, you should have a training 1 hour or 2 hours, because these are very delicate materials. So now I'm going to we're going to do the hands-on activities, and Sheila will show us. And if you want to come close to see how this works, it will be better. Okay. Okay. So let me.
How soon are you going to have your mechanism for training?
Tomorrow.
How soon do you think you'll have your training ready?
It's not for me, but yeah, you have to have a very okay.
And I'll show you why, because these are the AFM cantilevers right here, and you can pass them around. And if you try to look very closely, you will see an end, like a needle-like thing sticking out from one of the ends. It's kind of hard to see. Find something
What you're looking for?
like a pen or something for the board.
I can bring you. Give me a second.
Are those the probes that you had to get through the airport?
You're looking for. Do you know if we have a marker?
A marker?
To write on the board?
No, I don't know.
Let me go. I think I can find it downstairs.
And on the end of the needle is a very sharp probe. So you cannot even see that when you're looking at the cantilever. And this is the probe that comes in contact or whatever with your sample and is scanning the sample. So it is a very delicate system, but it is different from all other microscopy techniques like optical microscopy or the electron microscopy. You're not really touching your sample. So you can imagine these as your nano fingers by which you're touching the sample. And so you can see how you can move atoms around, move stuff around. And that's the importance of the AFM and the SDM, is you can actually go in there and manipulate objects and stuff, which is why it was a big deal at IBM when they invented the SDM, because they could arrange atoms, and then they wrote IBM, and, you know, that's a very famous picture now. So
Does this effectively become a tunneling microscope when you're measuring voltage? We're looking at tunneling potentials, or is it?
no, this is an atomic force microscope entirely. The electronics in a tunneling microscope is actually quite different. It's actually quite much simpler than an AFM too. So that's a different system altogether.
Okay, you talked about voltage differences. I didn't know though if you were looking at gap potentials or not.
voltage and current and stuff, but in this radio diagram, it's not. So, so what I'll do is I'll just start and get you guys an image really quick, and just to show you how the imaging is done. And after that, we'll sort of like open this up and change out a sample and everything, so you can see what's inside. Well, not inside, but what's inside the orange box. And so this approach button right here is for approaching my tip to the sample. Now, we cannot do this manually because it has to be very precise, and human beings are simply not that precise because we're working with a nanoscale here. So the software does it for you, and it'll bring the tip as close as we want to the sample, and there's a feedback loop in there which tells it when to stop and when not to stop. So this procedure is quite slow, but okay, approach is done, and let's start imaging then. I will explain all the parameters that we have. So right now, again, this is the
So it's scanning line by line. You see how it is creating the picture.
it's kind of exactly like how the TV creates a picture, like scanning it. It's
Yeah.
slower, of course, but that's what it's doing. You have this little scan cantilever moving across your sample,
Yeah.
scanning line by line,
Yeah.
forming an image right in front of
Yeah.
you. This is the topography, the surface topography. This right here is the amplitude scan of the tip.
The vibration
Vibration
amplitude.
And you can change, and this is the window right here. It's 20 microns by 20 microns. You can change it if you want to scan a bigger area. You can do so right here. So you can put this image size. If you want to do a faster scan, you can do that, or a slower scan.
Points per line resolution.
Points
This is
per
the
line.
lines per second. It is 0.5 lines per second. So this is the how long it takes to scan one line.
So if you make it slower, will it have better resolution, or?
If you make it slower, you will probably get better image quality, but you're also making it more prone to vibration.
Right, I was gonna say.
And-
Right.
Yeah.
So,
I'm watching the screen go up and down. We're on the second floor, so.
exactly.
Uh-huh.
And so I have left it at 0.5, which is probably ideal under these circumstances, but you can normally scan a little bit slower, like around 0.8 seconds or so if you want a better image. And the
If you have a big dump, then you cannot. It will not be able to vibrate as you wish. And if it's too small, then it will be,
Right. And so right here in the bottom window, you get the cross-sectional profile. And this window over here,
It's one line, no?
yes,
Uh,
that's
what-
like the cross-section as it is scanning.
Yeah.
This is the whole three-dimensional picture. And you can also create a three-dimensional picture over here if you want by right-clicking, going to chart size, and doing a 3D view.
Oh,
Yeah,
awesome.
yeah,
That's
this is
awesome.
incredible.
That is great.
That's neat.
Amazing. Well, sign me up. I will be there.
And you want bigger screens to show you the screen a little bit bigger.
Yep.
You can save this picture in a normal format, JPEG, and then you can embed it into a document. So it's very nice.
Make posters. We have a lot
I'm getting
of
so
nerdy
many ideas
posters
from my classmates right now.
in our offices of, yeah.
Yeah, for kids in high school and K-12, it would be great that you tell them do this and make the picture. They would get enthusiastic about it.
It's got to be meaningful to them. So I mean, that just looks like
They'll bring in
points.
their
Exactly.
favorite DVD,
Yeah.
their favorite movie or whatever, and then it's like, there's the image.
Yeah.
Okay, that's my new poster on my wall.
Right.
Right, yeah. So,
An image that they did themselves. So
My favorite scene.
and that was how we scan and get an image. So if you want, we can stop the image, and I can show you the insides of it and the intricacies.
Yeah, thanks for how it works.
and if we have time, show them the program, the SIP,
Okay, CIP.
so they can manipulate the picture.
Okay, we can do
Now, the software would have to be installed on a machine if we were
Yeah,
to use this, right?
exactly. Yeah, you have to be installing the machine connected to the device.
It's actually real easy, and you can install it on as many computers as you want. You just definitely need a dedicated computer.
Yeah.
Um,
Yes.
It's more getting permission.
Yeah. So if if you want to use it at your school, you can install it in your school, and whenever we take the machine, you have the
But I would
the software there.
put it on the server so we can just sign it in.
Yeah.
Does this have sign force measurement capability, or is it
It does.
only,
It
you
does.
can, so you can do sign
do it.
force?
That's an
Yeah.
additional mode, though. That is purchase an extra.
Oh, it is an
Yeah.
additional to be able to do it. Oh,
Right.
it's an option.
Yeah, but it has the capability of doing so. So,
Excuse me, I'm sorry to interrupt. Can I speak with you a little bit? Oh, thank you so much. Sorry about that.
so this is how, and I'll go over why it's shaped like this. This right here, this orange area is the scan head. That's where all the
Yeah.
electronics. Yeah, you can see the red laser light. That's the laser that Dr. Newton was talking about that gets reflected from the top of the cantilever. The cantilever is right here. If you want to take a closer look, you can just don't look right into the laser though.
Yep.
It's a very weak
Yep,
laser,
I see
so
it.
it's
Very
not
tiny. It's like kind of slides into place.
Yep. And
It's tiny.
this is the airflow shielding that I was talking about. So when you're looking at things at the nanoscale, like in the nanometers, even if you're talking by it, it
Right,
causes vibrations. It'll pick up all and every kind of vibration. So that's why this is what has the acoustics and the airflow and all of that a little. So this is what that's for. And right here is your sample. If you want to come by and take a closer look. That was my DVD that I was looking at. Of course, the image that you see up here is false color, and everybody asks why it's gold, and honestly, that's how they started doing it, you know?
They need some color for contrast.
Right,
Yeah.
exactly. So that's how it's, you know, when you see an AFM image in papers and stuff, this is what you're going to see, and this is what people are very familiar with. Of course, we have another software, which I will show you, which you can, I make my images pink all the time, so. And so if I were to change out a sample, I take my scissors
We have the samples
right
here.
here. So there's a little magnet over here, and your sample kind of sticks onto it. And that's again like an additional sort of a vibration stabilizing thing, so it doesn't move around when your sample is in there. And in this case, my CD sample right here.
Yeah. We bought a lot of samples with the that we can use. Yeah, many.
Okay.
We have a lot, and so you can program using it for. You can start by using the sample that we have here, but you can create your samples as well.
You can pass this around, and you can see there are like 10 different kinds of samples, starting from bacteria, the glass beads, the nanoseeds, all kinds of stuff. And these are the
Yeah,
pre-made
yeah.
samples.
Even nanotube we have there, so it's great. So
Yeah.
Stat. Culinary.
yeah.
A coulombic force, so would be from the difference of the charges, right?
What?
Use a coulombic force.
Yeah, the charge. Yeah, the charge, because material they have electrons, you know, and at this type of distance, the electrons actually interact with it, you know. Yeah, the repulsion. Yeah, this is the strongest force that you have there.
So you set this up ahead of time. Did you have to worry about leveling? Is it a long process, or?
No, I was setting it up when you guys came in.
Right.
That was
Yeah.
pretty much it.
Also, it's good for stabilizing the temperature. So This was loaded yesterday, so the sample and the magnet there will have the same temperature. Temperature, even a small change in temperature can affect this. You know, so.
This will cause drift and stuff. So what we did is we did a training yesterday, and I suggested that we loaded the cantilever and everything, and we keep it like that. So that's why I didn't need to do much today at all. Just
Is there an optimum temperature range?
I don't know. But I think if the sample it is at the same temperature, the room temperature, and the magnet, it's okay. It is the gradient which is important. I don't know if I think I have a slide that's showing what is the effect of changes in temperature with the resolution. Yeah. So.
So if you guys want to take a look at it one by one without touching the tools, and look through this porthole over here, you will see a reflection, and you can see the cantilever with the probe through this porthole. So if you kind of go like this, you will, just go ahead and take a look at it.
Not what you would expect. Yeah, isn't it? Yeah. Yeah.
All this picture that you generate, you can actually save them, and you can create a library of pictures. Okay, and very easy, and you can go back and read them, look at them again, and change them. You know, so it's a very good device.
When you set up the training, can you try to do it after school so that?
Yeah, I can do it after school or Saturday. Yeah, yeah.
Release time is
I know.
very hard to get.
Yeah.
Okay.
Yeah.
I appreciate that.
Yeah. These are different.
Oh, right, but still, oh my gosh, you're still, I mean, if you look at carbonatic and carbon
This is the amplitude. So this is the acoustic vibration, and how the
If your sample is magnetized, I mean, like you have to have the negative force and the negative force. Where's the positive?
The support of the sample it is in a support, and the support is it will not affect the magnet is not doesn't affect the measurement, no, because the sample is on top of a support.
Sample's on top of it.
Yeah,
Oh, I didn't realize.
a magnet. Yeah.
Well, like I said, I mean, even anybody that's, in IT or whatever, invite them in or whatever, because that's.
So when I looked through that eyelid, I saw basically that picture there, right? Basically, like little topology.
you see the cantilever with the
Okay, exactly. I thought I saw the silver square.
and you saw the sample underneath.
But on the sample itself, it looked like there was the topology. Was I actually looking at the bumps of the?
Yeah, well, I know, we've got that question going around or whatever. The thing that I said, though, is that the physics that we're doing, okay, is really mostly theoretical, okay? So when they say that, I mean, I can't do ballistics in my lab. I could ask somebody to go shoot something and go and bring it in and analyze it or whatever, but that's not what our focus is in our curriculum, okay? And so I said, instead of stretching that and saying that, well, there may be some criminal and bring samples in like that or whatever, but it shouldn't be something that's programmatic across the day, okay? Because everybody's doing it, and you know what I mean? It's hard to
You will not be able to see action by it.
It looks like there's like bubbles, or kind of like it's
Yeah,
it's above the.
I see that. I don't know.
I wrote that
You are looking at, you are not looking at the sample. The one that with the bubbles is not the sample. The sample is a reddish color.
Oh.
Okay, it's a square.
It depends on your sample, I guess. We imaged graphite.
Oh, I see. So that's the cantilever.
Yeah, that's cantilever. Yeah, so that's what it is.
That's interesting too.
I don't have it with me right now, but I can send you some images if you give me your email. I can show you some stock images
I'm
that
gonna
we
be
have.
measured by what the math teacher taught. I can do what's better analysis, but it's all math. So it's not even gonna, I can't even map it.
Like it?
Yeah. How much is it?
For the whole thing, if you buy only the basic, it's around 29. But we spend $41,000 because we bought everything, you know.
Yeah. That's really good.
Yeah. So we bought the software that we're going to see in a minute. Yeah.
Yeah.
So.
I mean, if you look at, what the majority of the curriculum contains, we're not supposed to be creating something so that it measures. So it will be something we're measuring. We're supposed to take multiple weights and then figure out how much of the weight is supposed to be
Sample.
And I don't know where these questions came from, that, where, I mean, I know one person that put in a what's Scholar question, and then what Scholar ended up being one person. We didn't even talk about it when we met in June. Yeah, but it's like, are we really teaching it at the high school level?
That's exactly the point I made, is that, on the other hand, yes, it's inherent in the program, but there's a lot of physics out there, a lot of criminal justice teachers out there that can't spell right. So it's all a matter of the delivery, and if you're not delivering it, in a physics perspective, then we're not gonna start making questions.
And all it is a bunch of word problems. That's what we do for ballistics, okay? And the word problems, like I said, are formula-based. And you can call that physics, but it's really just the application of the variables in its math. So it's not the science that we're trying to measure, okay? That's what I'm getting away from.
I'm with you 1,000%. I just was curious.
Oh, it's gonna be interesting at next week's meeting, because as a science group, we've been having an interchange with a reply to all, with all those questions and things like that, and, a lot of us are in the same thing, like where, CNA.
So it spreads out. Then you let it dry on there, and then you just test it.
Right. And the particles we showed you, I think you had a slide with the particles.
Yeah.
That's kind of what it is. That's
Yeah, you went so fast. We could go back to that.
Can we show them how to make measurement?
I'm gonna make them
Yeah,
like
yeah.
this baby question.
Okay.
Say that's not commensurate level.
Same
Say,
scale,
I
right?
know.
It is what it is.
It is what it is, exactly.
So do you see the difference between the CDs and the DVD and how spaced apart the data is as opposed to the Blu-ray, which was like so close you could barely see it, right?
Exactly, look
Now,
at
which
it.
one is this? I'm sorry.
This
This
is the CD.
CD. We're going to show. Shreya is going to show you how to make measurement. You can measure the size. So look at in 3 dimensions.
Yeah. 3D is pretty neat.
And even you look at the peaks and valleys, for CD versus,
Yeah.
there's not that much differentiation.
Is there some sort of way to see how deep those?
Exactly. This line profile right here will give you the depth.
Yeah.
Where's the scale on that?
It's cutting it off.
Oh, I see. So that's
So this scale right here is, so this is about 253 nanometers.
yeah. So those divots go like 100 nanometers.
Yeah.
Or 200 nanometers.
What?
This is a mastered CD, it's a printed one, not a burned one,
It's
right?
actually the stamper, the CD stamp, yeah.
Oh, it's
yeah.
actually, it is the
Right.
Yeah.
And
Now, oh, okay, 'cause the burn one, you
The
don't
burn
have it.
just changes the diffraction,
Yeah.
the mix up diffraction with the plastic.
so going back to this, I want to show you how to do some very basic measurements on the software itself. So, like when you're imaging, your students are not sitting around, because you all know how you get them to do that. So, so this is what. So when you right click and you can go to tools, you can do some basic functions, like you can measure length, distance, angle, cross section area. You can correct the background plane, because you see there is a tilt to the background plane over there, which is a false tilt, because we know it's not tilted. So that's what you need to do, is you correct the background plane. Yeah, you can zoom in if you want to. If you just want to reduce the noise, you can do that. So I'll show you some like a basic, say, measure distance. I want to measure the distance between 2 points. I just clicked on that option. I want to say measure the distance between this point and this point right here. And it's cutting off the, so I'm connected to the projector, that's why it's cutting off the screen, but there's a panel that comes up here which shows the distance, the perpendicular distance between these 2 points.
Is that a music CD? Or a music CD?
Yeah, I can take a regular data CD. Just go to Home Depot and buy a bunch of.
My grandmother used to have a home playing, self-playing piano, and the reels look just like that.
Oh yeah, similar to these are the actual data. This is a DVD. So this is actually the zeros and one where you can listen music to. So.
You want to measure an angle somewhere? If you have a sample that would require you to have an angle, you can just do an angle measurement and read out the.
Yeah. Especially if we can see a crystal, you can measure the lattice, okay, and the angle of the lattice. So.
Your software is unlicensed. You could have post-processing, and every student could have it on their computer. And once you took the image, you could just have them all open the data file, and they could do all their own individual post-processing.
Yeah. Well,
Kind of like do it up on the board while
take
it's
the image once
processing,
and then let everybody
and
else.
then send it to all.
but do you have the software to handle it? We have one, but we have only one license so far.
It is a license.
So the post-processing software.
You-
Well, okay, there are certain levels of. Back scanning again. Okay, yeah. Just let me stop this for a second. So there are 3 types of post-processing that you can do. You can do the post-processing on here itself, and for that you just need our software, the NanoSurf software, and you can download it to as many computers as you want. There is a free version. There's a free software called Guidian, which does some basic post-processing, and then there is a fancy, like a really nice post-processing software which Dr. Michelin has, and that is licensed.
That's a license, yeah, but it's terrific.
Really differs in user friendliness and capabilities, but depends on how much in depth you want to go to, like, or how much you want to,
But all of this is all your built in.
Yes.
Yeah, this is the.
This is our software,
Yeah.
and that you get with our CD, and you can install it in as
And you
many
can do it
computers.
post-image, right? It doesn't have to be just a line. You can save all the data.
Yes, all of the data is saved in the gallery, which is hidden, but it all gets saved in the gallery. Even if you close it and reopen 10 days later, it's all going to be there. You can rename it, save it as something else, and all that kind of stuff.
Can you try control with the negative sign and see if we can use? No, not quite. Sometimes we can shrink it.
Right, it's not doing it because, like, you see this panel over here, a similar panel is there on this side, which is not.
I think the projector maybe.
Yeah, just cut it off. So.
Yeah.
When you were looking for a perspective scale, as a player.
Oh, there you go.
There you go.
Well, then the CD will, when you look at a very similar data track.
That would be pretty, yeah, that would be neat, actually.
So you see right here, you can see the tool status over here.
Length,
And right now right now what I was measuring here was the cutout, the cross section. And so along the line it's giving you the roughness.
Okay.
So, you
Along,
can
that's
see.
the pattern.
Yeah. And here's the gallery. So
You can
these
keep
are
them all
the
the time.
images,
Yeah.
and these are what we imaged yesterday. It's all still saved over here. If you want to say this particular image, you want to rename it, you can do that. If you want to delete it, you can do that. And the good thing is all the parameters get stored with it.
Yeah.
So if you want someone
If you want to
replace
analyze it
yeah.
later,
So these are the parameters of the device. So if you want to reproduce it, here you are. The kids who can reproduce on. You know.
And there's the video, there's the live video over here, and I'll show you something cool. You can actually see it. Yeah, it's too cool.
Yeah, this is.
So you could just see it moving while it's scanning the surface right here.
And what is that called? That's under, how did we get to that? I'm just like,
That's this panel right here.
no, how did we get to that,
Oh, the
video
video.
view?
Well, right here is a video option.
It's at the bottom, okay.
So
Okay, that's
you
okay.
can have there's a help where you can, if you get stuck, you have all the manuals, the gallery, the
Okay.
tools.
Yep, the folder options are just at the bottom.
Right.
So in your device, what is moving? Is it the scanner that's moving or?
no, the cantilever.
Cantilever.
Cantilever's moving back and forth.
That's different than most. Is that true or?
Well, there are some, I think like Decos and stuff, they have the base that moves, but Agilent and Nanoserve is the cantilever that moves, and that's what makes more sense, because it's moving the X, Y, and Z direction. So, yeah, that is what it is.
Yeah, this is a beautiful device. So
Thank you for sharing it with us.
yeah. Well,
And real quick, just to go over SPIP, the software that I was talking about.
this is the license. We'll see how.
Oh, do you have the dongle?
Yeah, I should have it in. Yeah, inside the envelope. What is the other machine? Yeah,
In this one?
yeah, this one. Yeah. Yeah, I think inside here.
So yeah, you need a specific dongle for this.
Yeah, you have to have this. But if we loan this device, can we put it in another computer or no? The software.
I don't know if you can download it on different computers,
Okay.
honestly. Like it's
Because I was thinking that if we have this,
right.
So it's only dongle enabled? There's no way to
but yeah,
There is a temporary option. You can do it for like, I don't know, for a few weeks or so. But if you want to use it on
uh,
by seats.
yeah, yeah. But yeah.
5 people to be logged in.
Yeah. But we bought, we are expecting, I bought another laptop especially for the AFM. So when we ship this, we'll go with the computer. So, but you cannot install it in more than one computer. But
The training sessions, would those be a group training session, or would that be something that?
for the training, a group, yeah. Erin will call, yeah. But we are going to offer as many as we need, okay? So.
That you want to do it.
I hate doing that, though, I know.
I know,
I've
that
done
is
it
like-
unfortunately.
I look at the.
I decided to go back and say, hey, I want to look at that. Oh,
I can't, right?
So this, in addition to a lot of different stuff, is, you get a cool 3D version. You can like move it around, like animations and stuff. Change the color. And see?
Oh, there's your key.
That's what most of my images look like.
I think,
from the bottom.
I was thinking along those same lines, like how you people, when we were talking about it before. But if you can make samples, just the making of the samples.
Plus you can print out images.
Oh, you can print it out in 3 dimensions, yeah.
So the kids can have their own
Yeah, because
images.
then you
Yeah.
can actually see it.
I was talking to a professor in a community college in Oregon, Schmeckeda Community College, and like their art teacher actually takes the AFM images and they like change colors and stuff like that, and
Yeah.
they incorporate it in their art class, which is I think
Like the,
really
Yeah.
really cool.
like the nano galleries.
Yeah, like a nano gallery, yeah.
Exactly. We do that with the SEM too a to take it outside the site.
Who we have experience with that was collaborating with art people?
Oregon, it's called they're called Chemeketa Community, CHEMEKTA. Lady Dorothy Moore, and she was involved in a lot of the curriculum development, although she had no science background. Her PhD was in education, so she had to learn how to use the instruments, and that's why she has this perspective, you know,
Right.
hey, let's take it to the art teachers and stuff.
Well, I have another idea too, because a lot of times the kids want to share things via a web page, right?
Yeah.
And so if every student that was at a computer while we're running everything here was starting to design their web page, okay, for a component of,
Yeah,
okay, this
absolutely.
here, so that they were responsible for teaching others about one component about this, then they could be working on that while that's running, and then they, you know, they still look up and watch and things like this, but then everybody would be saving their page. You can put that together,
Yeah.
and then you can share it.
Yeah.
Do you have a butterfly wing? I've seen that a lot.
I know I don't have one image right here. We have done that in our lab though, and that's really cool. Like, structures. Yeah.
Oh, we never find those. Never.
Right.
Yeah, we've been like
If they're live, you have to set them free. Good karma.
Well, we are going to buy very soon from Nanoscience an SEM. This will be bigger. We'll see how we can transport it. We will make it available for you probably in a couple of months.
Okay.
And we are going to bring Shredder here again for training. How about that?
Sounds, hopefully in summer.
Yeah, we'll make sure it is a spring or something.
Are you getting the Phenom one they have?
Yeah, it is a Phenom or the, yeah, I think the Phenom, yeah.
That's the one you
Yeah, we're going to buy that.
So I have some standard AFM pictures and AFM images from our lab right here.
So they save them as
This is the 3D images of the CD. This is our grid, it's a calibration grid.
Oh,
So this is what we started out with at the training yesterday,
Yeah.
just to make sure everything was okay. This is, I think, like some silicon something from the fabrication lab. This, you'd be surprised, but this is actually hair.
Wow.
It's actually human
Hair?
beautiful.
Like how hard would it was for us to prepare a sample?
Well, it was actually a little difficult because the hair is very cylindrical. You know, if you look at it on the DSM, it's like a cylinder, right? So we had to like cut out a cross section and stick it on and everything.
Cut out a cross section of hair.
Yeah. Like, you know, slice it. And so, because if it's very cylindrical, the tip cannot, you know, get the whole,
How do you cut out a cross section of hair?
like, under the microscope, it's very fine.
So we're looking at cross sections here.
I think they use like a sort of a profiler or something to just slice it. I'm not sure, but they used an optical microscope to look at it, and then they somehow managed to.
You don't have to use a knife, but you can, you know, reduce it by with sandpaper or something. You can mill it, yeah.
Cylindrical cross sections, is that what we're looking at here?
This is just a cuticle layer.
Yeah, that's just the top layer of hair. This is what it looks like.
So when you
You know, I
prepare
have
this
worked
last
at
night,
You can.
It doesn't always have to be flat, but if it's too rough, you know, it's a problem.
like we're seeing, like we're sending us basically a 2D flat.
Yeah. All AFM images will be inherently two-dimensional, but since you have the the topographic information, you can combine that using softwares and make it a three-dimensional image.
Okay, I was thinking more along the sample preparation.
Oh, okay.
Is that the sample preparation lab that is splitting there?
Yeah, we're going to do sample preparation, but very simple here, okay? You take tape paper double thick, you know? Yeah, and then you put it there. But there are other microscope that to make a sample is an art, you know. So you have to, but for this one, it's anything which is flat, you can say. You know.
So those are just some typical samples, and yeah, there's a bunch of curriculum. So knock yourself out.
Yeah, that'll be interesting for us to see the curriculum before we come to the training, so that we can say,
Yeah.
we're really interested in doing this lab.
Yeah,
And that way we can, speak to you about it. That would be good.
Yeah.
And where's the curriculum located?
It's right now. It's with Dr. Michelin on the flash drive right here.
Yeah.
You can share it.
I can share all this. We can distribute them, no?
Yes, because we haven't developed it. It was developed at University of Washington and at various other universities, and they're willing to share. So we just kind of
Send
give it out. Yeah. And
Yeah.
so this is the optical media experiments that we developed, and this is your Blu-ray, DVD, and CD experiment.
Very good. Awesome.
And yeah, we have.
You can ask the student to measure and the distance between the bits, and you know.
So it's going into how it's doing all the
My third
measurements.
quarter project.
Right. Troubleshooting and how it's reading it. So it talks all about the technology. And yeah, and then the calculations at the very end, right here. Shows an example of calculations that we did. Oh, and then it goes into various problems that you can see. All the noise up top, like the periodic noise and everything, and how you can possibly get rid of them. If there's dust, what do you do if your tip is damaged? What do you see? And some calculations which will use the capacity of the disc.
For the kids,
Which you
great.
guys are not supposed to see now, because this will be on your quiz. But yeah, so
Yeah.
we have all of these materials to help you get started.
Thank you.
Yeah.
And
Oh.
some videos too, that you can watch.
Yeah, it's a very incredible tool to instill in the young people. They love. They give them some impact.
They will remember that. They will.
Abe, you said you have this stuff and you'll be able to share it with us. How will we know when you have that we can look in on?
I'm going to call for training first.
Yeah.
And we're going to create something like a certificate that you are trained, because we don't want to send it to anybody and then and the manual and say you. Yeah. So very soon. But if you think,
How will we make sure we learn? I mean, in each of our busy schedules, that kind of stuff. Should we call you? Will you send us?
you can call me, or you can send an email to Erin and to me and copy me. Erin will be handling the logistic of the. If you don't hear from me or from Erin for a long time, say 2 weeks, send us an email.
Perfect.
Don't worry bothering us. We like that. Okay. And you said after hours is better for you guys. Saturday morning, can you do that?
Yeah,
Okay.
outside of school days,
Yeah.
Saturday is better than
Yeah, perfect. You send me an email if I am behind 2 or 3 weeks. Send me an email. And you guys are going to learn next week. I think Fred is going to ask you to do an experiment, take a CD and the Blu-ray and measure the difference of. So you will learn how to use it. And be careful with it, okay?
Yeah, don't break it.
No, these are my students in the semiconductor manufacturing, and they handle, wafers and lithography, and this is very delicate stuff, okay?
Can we actually examine the diodes that we made, or the lithography that can we actually examine the diodes we made?
The diode?
From last semester, the 65 class? When we were doing the masking and the.
Yeah. You want it? You want it back?
No, he wants to examine the diode. He wants to analyze it.
The diode that you created last semester?
Yes, is that going to be worked into this?
Yeah, but you have to break the wafer, of course, in a little piece.
You can't just.
Yeah, because it has to be it has to put in sample,
The last cool
You
thing
gotta
is it
destroy it.
fits all into this.
That's amazing.
The whole AFM fits right in here, and I carry it with me like when I'm flying and everything. And somebody once asked me, "What is this?" I was like, "Guess," and he's like, that a rollout dance floor? Nobody can ever guess that an AFM is in here.
Nobody, most people don't even know what an AFM is.
That's
So,
true.
Oh my gosh.
that's so, thank you so much.
Yeah, so thank you for saying that. Thank you. Yeah, so you have now a new tool for your classes, okay? Hopefully you will use it, yeah. Yeah. Excellent, very good. Oh, yeah, thank you. I copy you from your side, but yeah. Let me see. We put here the samples only, or
Yes, I
yeah,
put the sample.
and then
I'm very intrigued by the sample preparation part of this. It must be quite a skill to take all the different samples, especially when you're working with vacuum.
Oh, yeah. It can range from really easy can samples to synthetic days of samples.
I realize some of these microscopes are the size of cars.
Oh, yeah.
So I know that
Yeah.
differences.
A UHV STM can like fill up half the room. Like the older ones especially, because the electronics in them, which I didn't go into, but you know, it's different electronics depending on what you use. It can be really which can be very important. Well, you learn
Black magic.
you like it? Okay.